From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. It's hard to believe that after today we have only 2 classes left. Is that right? So the final exam is scheduled for May 14th from 8 to 10. I remember a week or so ago a couple of students came by and they had a problem with that date. Has that problem gone away, or what's that? Okay. Are you still interested in switching? Or is everyone else here interested in switching? This will turn into probably a problem here this morning. Does anyone want to volunteer when you'd like to have the exam, other than next year or sometime yet this year? So May 14th was the date it was scheduled for.
Wednesday would be okay.
The 13th, May 13th at 8 a.m. Does anyone have problems with that? Bad luck. Well, it's not Friday, it's a Wednesday. So I think Wednesday the 13th is good luck. I think I read that someplace. You have an exam then, so that's not good. That's what I was worried about. We're going to run into lots of problems there. Do you have another date then? Tuesday, the 12th. That's definitely good luck day. Does anyone have a problem with Tuesday the 12th for the exam? Tuesday's great. Can't believe it. Well, let's see. So exam Tuesday, May 12th, 8 a.m. Going once? Going twice? Okay. I will check on a room for that. May 12th, 8 a.m., 10, someplace. Okay? Well, I'll get back to you next meeting, next class to see, and you can think about it if anyone has a problem there, but hopefully not. So May 12th. Okay, last class we were talking about holography, and so we'll talk about that some more today. And I think we were up to section 17.5, if I remember right, which is on light sources and recording materials. So 17.5, light sources and recording materials. Well, for part of this, I'll just go to the view graphs that you got earlier in the semester. And the first thing we can say here is that we need a good coherence length source. And so we're probably going to go to a laser. I mean, the early holograms that Gabor made, I think were made using a mercury source. And back in 1947. And then the laser came along in the early 60s. And you still see papers on making holograms without using a laser, but it's difficult at best. So we're going to use a laser here. And sometimes if you're making holograms of something that's changing, you need to have a fast exposure. And so we go to a pulse laser, ruby laser, or maybe a frequency doubled YAG laser. But most of the time, the 2 most common lasers are the helium neon laser, working at 633 nanometers, and the argon laser. The helium neon, the problem with that is that it's generally low power, and the beauty of the argon is that you can have lots of power, a few watts if you want, depending on how much money you have. And several different wavelengths that you can have. I guess if I'm going to say things in nanometers, I should get rid of that 5 there. And it's convenient sometimes to make the holograms at different wavelengths. Sometimes a krypton laser is used. It gives you light out in the red. If you're making holograms, 3-color holograms, you like to reconstruct using, so you have color holograms, you would probably pick a couple of lines from the argon laser and then a line from the krypton to get the red light. And then dye lasers are convenient sometimes because you can change the wavelength that you have. I think quite a few of you said you had made holograms. What did you use? Helium neon lasers, or pretty much, or what else? Argon lasers. Okay, good. Okay, so you like to have coherence to make life simple. Now the next thing we want to worry about here is the recording material. And before we talk about the recording material, let's think about some of the characteristics we want. And probably the one that is of most concern to us is that we have to be able to record the interference fringes. And if we think for a second, when we interfere 2 beams, if we go back to, this is a view graph we had much earlier in the course. If we interfere 2 beams, we have the spatial frequency of the fringes given by these 2 expressions here, and then we have the plot. Plot 1 is for the more symmetrical case where we're bringing in light at plus or minus π/2. And then plot 2 is where one beam is coming in at normal incidence and the other beam is coming in at angle phi. And for the numbers here, I've used 633 nanometers. But the point to make here is that the frequency gets high very fast. And if we go up to, say, 45 degrees between 2 interfering beams, we're up, well, more than 1,000 lines per millimeter. And so the one requirement we certainly have to have is to have very high spatial resolution of the recording material. And I don't show it on this plot, but let's think for a second here that one way of making a hologram, we'll talk about reflection holograms later on, is that, say this is our recording material. We may bring a beam in from one side here. So let's say we have a plane wave coming in here on this side. And then we could bring in a beam from the other side as well. So now these 2 beams are going in opposite directions. And the fringe spacing in this case so let's say the wavelength is lambda. What will the fringe spacing be here? Distance between fringes is, if we're going in exactly opposite direction, half a wave. So say they're in phase here. You know, if we go this way half a wave, one path is increased by half a wave and the other path is decreased by half a wave, and so they would be in phase again. So the fringe spacing is the wavelength divided by 2. And so if this were a wavelength of, I'll pick a number that I can divide easily, 500 nanometers, lambda over 2, 250 nanometers. And so how many lines per millimeter is that? Is that 4,000 lines per millimeter? 4,000 fringes per millimeter? And it gets even worse than that, because this material has some refractive index of n. And so it's the wavelength inside the material that counts. So it's wavelength over 2n. And so now we're getting up to maybe 6,000 lines per millimeter. So certainly in this case, when we're making these so-called reflection holograms in the extreme, we look at the closest, what's the closest the fringes can be. They can be lambda over 2n, or 6,000 lines per millimeter. So whatever recording material we use has to have a very high resolution capability. Fortunately, there are recording material out there that will resolve 6,000 lines per millimeter. Maybe you can guess the bad thing that normally happens when you go to high spatial resolution recording material is that the sensitivity gets low. And so we'll look at some numbers here as we go through here, but the sensitivity will go down, so we need more power from the laser, or we need a longer exposure time. So if we think about what are the common recording materials, and there are probably, this is maybe half of the materials that people actually use, but these are some of the more common ones. Certainly the most common one is photographic film. And fortunately there are several films available that have very high spatial resolution that are good for making holograms. And I'll steal a table here from Goodman's book. We'll come back to this. We could zoom in. This is an eye test, maybe. Anyway, this is on page 347 of Goodman's book. And kind of over the years, well, early on anyway, the most common recording material was Kodak film 649F. And the 649F has a thickness, it says here 17 microns. Number I more often have seen is 15 microns, but something like that anyway. It's sensitive in the red, as long as we stay below 700 nanometers. So it does work with a pulse ruby laser, and it works pretty well with a helium neon laser. And it has a resolving power of greater than 2,000 lines per millimeter. It goes out to 4,000 or 5,000 lines per millimeter at least. And I guess he has cycles per nanometer, but it should be cycles per millimeter. I guess this is wrong here. A bad thing about this film was that the sensitivity is bad, and probably these numbers, maybe just by looking at these numbers, you're not going to realize the sensitivity is bad, but take my word for it. Once you begin using this film, you'll find out that, and a helium neon laser, you find out you need long exposures. So it's 80 microjoules per square centimeter. But anyway, the 649 film is a good film, except that it's slow. AGFA had a good film, and it's still in Goodman's book, but we tried to buy some AGFA film a couple or 3 weeks ago, and found out they no longer sell it. But I'll still talk about it for a minute here, because I can't believe it. Someone else, I think, will buy the licensing rights or something. I can't believe it's going to disappear, because it's excellent film for making holograms. And they had the film that was sensitive in the red, which was 8E75 or 10E75. And it had resolutions out here where the 8 went up to, they said 5,000 lines per millimeter, and the 10 went up to 2,800. And then they had a blue sensitive version of it called 8E56, which used with the argon laser in the blue, and that was about 5,000 lines per millimeter. The sensitivity here, the AGFA film became much more popular than the Kodak film because the sensitivity was better. Up here we were taking like 80 microjoules per square centimeter, and the 8075 was like 10, 10E75 was like 1, and the 8056 in the blue was like 25. So this was more sensitive than this. So it became much more popular than the Kodak. So what do you, and the Ilford down here, I don't know much about that. I don't think it ever became very, very popular. But anyway, maybe I ask you, when you made holograms, what film did you use? Do you remember? came out of some yellow box, or so it was Kodak film, or an orange box, I guess it was. It's Agfa film, so whatever. Anyway, so Mike North Morris was trying to buy some Agfa film for us, and he found out they didn't sell it anymore. And he went out on the internet. So what do you use now, I guess is the question. So he went out on the internet, and this is what he found here. So this is off the internet. Agfa stopped manufacturing holographic film. But the thing is, the Russians over the years had developed some superb, absolutely superb holographic film. The problem was you couldn't buy it. But now you can buy the Russian film. And as I highlighted down here, it's 5,000 fringes per millimeter resolution, more than that even. It's sensitive in the red, although they claim that coming out with sensitivity in other wavelengths. And if we go here to another page, says the sensitivity is about 30 joules per square meter. I guess the other stuff was per square centimeter, so that would be, 30 times 10 to the minus 4, or 3 millijoules per square centimeter. So that's pretty good. That's down in the range of these guys here. Pretty good. What's that? Microjoules? Oh, so it's not so good. Yeah, it's not so good. You're right. These are microjoules. Glad you're on your toes today. So this is not going to be very, very sensitive, is it? But very high resolution. As I said before, high resolution goes with low sensitivity. Anyway, we actually bought some of this, and it came 3 days ago, I guess. So we're going to try it out. But I guess, as you point out, it's going to take a lot of exposure time. So that will extend Mike North Morris's dissertation time, maybe, by all the exposure time this is going to take. Yeah, okay. And of course, this, you develop it differently from what you develop the U.S. or the Agfa film or the Kodak film. But anyway, we bought some developer too. He says the documentation leaves some to be desired, and so we'll see what happens this summer. Anyway, while Mike North Morris was checking out for this film, he found another thing which has nothing to do with this course, but I have to show it here anyway. How many of you surf the internet when you should be doing your homework? Yeah, okay, a few of you. Anyway, I love the internet. Anyway, he found on here the Internet Museum here, Webseum of Holography. And I had to go check this out, of course. It's actually kind of interesting. And one thing they have is this theater here where you can look at old TV programs they had on holography. And it's hard to believe they used to have TV programs on holography. There were not a lot of them, but anyway, you can enjoy these and find out, that come June 6th, we have a laser and hologram exhibit in Pennsylvania, if anyone's going to be back in Pennsylvania. Anyway, it's kind of a neat site when you play with it, and it's www.holoworld.com. Okay. So anyway, as I said, the film is the most common way. I'm sorry that the Agfa film has disappeared, and I hope the new Russian film works out. But I have to believe that someone is going to buy licensing rights to the Agfa film. It may not have been a large enough market for Agfa to be in, but hopefully someone else will take it over. Next on my list anyway here is the photoresist. And this is a thin phase hologram. Photoresist technology certainly has been developed extremely well for the electronics industry. And you simply expose the photoresist here to your holographic fringes. It has very high resolution. You go in, when you process the photoresist, whether it's positive or negative photoresist, a portion of it is removed, either the portion that was exposed or the portion that wasn't exposed. And so you end up with a relief type hologram, phase hologram, which gives you good sensitivity, good diffraction efficiency, I should say, being a phase hologram. It has high spatial resolution, no problem there. And so that works out to be a pretty good holographic recording material. The next one, dichromated gelatin, is kind of strange stuff. I don't know, any of you like eating Jell-O? Because that's pretty much the same here as this. You can use your Jell-O to make holograms, I guess, if you don't like eating it. I don't know of any place you can go out and buy dichromated gelatin, although there may be some place out there to get it. But typically what you do is you take film that has very high spatial resolution. Probably 649F is the most common film they use here. And the first thing you do is you fix the film, which means you remove all the silver. So before you expose it, you fix it, which seems a little strange. But you remove the silver from it, and what you have left is gelatin. And then you expose that. And again, it has very high spatial resolution and very low sensitivity. In fact, I have some numbers here that for dichromated gelatin. It's going to be even worse than this Russian film, probably. So dichromated gelatin. If we go to wavelength, generally use the shorter wavelengths here to have any sensitivity. 488 and 5145 nanometers. Sensitivity is about 50 to 100 millijoules per square centimeter. So again, if we go back, and as you pointed out to me, that these guys here are 80 microjoules or 10 microjoules or 1 microjoule. Here we have 50 to 100 millijoules. So very low sensitivity, but very high spatial resolution. The other thing I should have mentioned before, when you're using these holographic films, it's nice to have something that is sensitive over only a portion of the visible spectrum. So you can use a safe light, and makes life so much easier being able to see when you're making your holograms, and also when you're processing your holograms, especially if you're guessing the exposure. It's nice to kind of look at it every now and then as you process it to get the right density. If you overexpose, then you can remove from the developer sooner. And so it's nice to have something that's not sensitive across the whole visible spectrum. The last guy, the recording material, and maybe I should say recording device in this case, that I was going to talk about here, is a thermoplastic device. And this is something that I plugged with a number of years ago, and it's a great device, very convenient for holographic interferometry, which we'll soon begin talking about. And the device works like this. And this again comes from the view graphs. So if we could zoom in a little bit here. Okay, that's good. So the device here consists of a substrate, say a piece of glass, and a transparent conductor here, a photoconductor, and a thermoplastic thing here, and then something up here to with a high voltage on it to essentially spray charges over here. So maybe 10,000 volts. And so what we would do is the following, is that we would first charge this up. So if we could zoom in on the top one here, then I'll move it around so we can look at the different portions here. We're first going to charge this up, okay? And then the second step is that we're going to expose this. And as we expose it, it's going to cause some of the electrons to move across the photoconductor here. And then we will charge again. And so now what we have is a potential variation across here that depends upon how we expose this to light. So now what we do is we heat this up a little bit. And generally we just apply a little voltage, a little current here to this, and heat it up. And so this thermoplastic is going to deform. And so down here is a hologram. So we don't have to take this device away to the dark room and mess around with chemicals or whatever. But we can develop it right in place just by changing the voltage on it and heating it up a little bit. And it's a phase hologram, so it has pretty good diffraction efficiency. And the spatial resolution of this depends upon the thickness of the thermoplastic. And it does not have very good spatial resolution, very good resolution at low spatial frequencies. And maybe you think, well, maybe that's bad. But that's actually good. If we think about, remember this intermodulation noise that we had, the self-interference term, where different points, light from different points on the object was interfering with itself? The object was interfering with itself, I should say. And so that's producing low spatial frequencies. And so a nice thing about the thermoplastic material is that it doesn't do a very good job at recording these low spatial frequencies. So the self-interference term is reduced. The other thing that's really nice about this is now you make your hologram, okay, and you look at it, well, it's not quite perfect, okay? So what you do now, I mean, if you had to go through the photographic process, you'd probably say, well, it's not perfect, but it's good enough, okay? But here what we can do is we can just apply a little more heat to this, and we're going to erase it. Okay, it's going to deform. So now we go back to the beginning, charge it up, and we go through the steps again, and we make another hologram. And we keep repeating that until we have this masterpiece that we want. So this device, thermoplastic device, is extremely useful, and when we soon get to holographic interferometry, we'll see just how great it is there. The problem with this device right now is that, well, it used to be sold by Newport. So I recently went to the Newport catalog to see what the recent price was, and I couldn't find it. So I think they're not selling it anymore. And there used to be another German company selling one of these. I can't remember the name of that company right now. Does anyone here have any experience with a thermoplastic device like this? And I was going to ask you where you can buy one now. Anyway, next time you're web surfing, can't decide what to look for thermoplastic devices for holography. And then when you find out who sells it, come and tell me. 'Cause it was a very, very nice device. These holograms are not meant for something you're going to keep for 20 years. They're meant to where you're going to make a hologram of something and then analyze that and then erase it. And certainly a device like this, if you made one of these holograms, you wouldn't want to put it in your car in July in Tucson, because you'll erase it very nicely as you heat it up. So anyway, they're not for archival purposes, but they're very nice when you... it works at high frequencies. Yeah, it depends on the thickness here, but you can't do 10 lines per millimeter, but you can do 800 lines per millimeter. Okay. It has a little band pass with it that, it might work from 400 to 800, or you change the thickness, you can make different ranges that it will work over. So you know what frequency, when you have one of these, you know what frequency it works over, and so you just select the angle between the two interfering beams to produce fringes at that frequency. Okay. So that's everything I was going to say with 17.5, I guess. 17.6 is on volume holograms, and I'm going to do that, but I'm going to do 17.7 first for some crazy reason. As I think about it here, I think it makes more sense to do 17.7, and then I'll come back and do 17.6. 17.7 is on applications. Well, I think I told you back in the heydays of holography, in the mid-60s, people had all kinds of fantastic ideas for applications of holography. Most of them having to do with three-dimensional movies and three-dimensional television. I don't know, how many of you have seen a three-dimensional holographic movie? Oh, no one. Okay. Yeah, they actually made a couple of them. I think they lasted maybe a minute or so each, but it never quite worked out. And probably, the real problem is that there's so much information that you're storing. If you really are making you're going to make a three-dimensional image for each frame of your movie, there's tremendous amount of information that's in each three-dimensional frame. So it never really made it there. And there are a lot of other areas. I'll write down a few of them here, and then we'll talk about the ones that really have worked out better. Well, optical processing was a big one. And the idea here, and I think some of this is described in Goodman's book, and I'm not going to talk about it here because it never has worked too well, other than to give you the basic idea of the theory behind it is very interesting. And that you take a picture of something, and you have a certain, well, we talked about certain optical transfer function when you take that picture. And so the idea here was to then go through, and when you reconstruct this with coherent light, and you take so we'll take a Fourier transform of the picture you've taken. We can go into the spatial frequency plane and put a filter in there that we'll call an inverse filter. And basically you are making a filter that goes as 1 over the optical transfer function. And so you're dividing through by the optical transfer function. And so you have the optical transfer function divided by the optical transfer function, you end up with unity. So you remove the effects of the optical transfer function. And you can make this filter using holography, and I think it's described in Goodman's book very well. The real thing that always happened on this is that you get so much noise by going through this process. So much noise by going through the, using coherent light, that you see publications of, this is, on the left-hand side, you would say this is a picture before optical processing. And on the right-hand side, this is a picture after optical processing. And you look and think, maybe the journal got the two pictures reversed. It was hard to tell which one was better than the other one. And so I think, it's hard to compete with a computer, and any processing here now becomes digital processing, and the holography part of it's pretty much gone away. We have data storage, and people are still working on holographic data storage. Ray Caustic is one. So I better not say anything nasty here, because Ray still has a lot of interest in this. And maybe something will come of it someday, I don't know. But it's hard to compete with the optical discs, hard to compete with the magnetic storage devices. And the holographic data storage hasn't done extremely well. Imaging through, I think this is also in Goodman's book. Aberrating media. And this was actually Gaskell's dissertation, so of course I'll have to say a few nasty things about this. But the idea is that you go through the atmosphere, for example, and you get aberrations due to the atmosphere. And what you can do with the holographic process is you get this conjugate image that we talked about, so that has opposite the phase, and so maybe we can correct for the aberrating media by going back, sending the light back through the media, correcting for itself. The real problem here has been that in order to make this work, you have to have some equipment both at where you're taking the picture, and you have to have some equipment at where the object is. And I figured if you could always put the equipment where the object is, maybe that's where you should take your picture and not some distance away. But anyway, Gaskell got his PhD for that, so give him credit for it. Okay. Now, maybe more interesting ones are optical elements. I hate to think what Gaskell says about me in his class. I don't know. The fortunate thing is that he has you first, and I get you second, so I have the last. Try to have the last thing. This is actually a very useful application of holography. Certainly making diffraction gratings. I mean, a diffraction grating and a hologram are very similar. So you can make superb diffraction gratings using holographic techniques. And you can build into these diffraction gratings any aberrations you want or any lens functions, optical functions you want. And so maybe, a classical way is you have a lens and you have a diffraction grating. Using holography, you can put the lens and a diffraction grating together. And so that's a kind of useful application. Two that I want to talk about more here are interferometry, holographic interferometry. And then, so we'll talk about that next, and then we'll talk about displays. And I think most of the other items on the list I won't even mention here. But holographic interferometry has become something that's extremely useful. And I'll go to the view graphs here. We're going to talk about three types of holographic interferometry. And what I'll call here, the first one is we'll call real time. Second one we're going to call double exposure. And the third one we'll call time average. So let's talk about real time first. First we'll go to a setup here. So we have some object here, and I don't know what the object is here, but doesn't matter. In fact, that's the great thing about holographic interferometry is that we really don't care too much what this object is. It could be this desk, could be the wall, could be your face, whatever. Okay. We're going to make a hologram of it. Okay. And then we'll process the hologram, or what's really nice is to have the thermoplastic camera here. So we could make the hologram and not have to go away to the darkroom, do the processing. Or sometimes people would actually put a little tank here and put the photographic plate inside the tank, and they would develop right in place. In any case, we're going to make a hologram here and process it, and then put it back in place. And when we illuminate this with this beam, and if I remove the object, if I look through here, I'm going to see the object anyway, because I made a hologram of that. Okay, so I'll see the object. Or if I block the reference beam here, I look through here and I'll see not an image of the object, but I'll see the actual object. So if I have both the reference beam illuminating here and I'm illuminating the object, I'm going to see two images of that object. One as recorded in the hologram, and one as it actually exists at this time. Now let's take this object and let's deform it a little bit. Maybe we heat it up, or maybe we just put a little pressure on it or something. We deform it. So now I'm going to see the deformed object and the object as it used to exist and as recorded in the hologram. And I will see interference between the two. Okay? And so I will get interference fringes that are going to tell me how the object has changed. Now this object can be a very rough object. And you think, well, interferometry with rough objects, you have problems. But the idea is that the roughness is the same both in the recorded image of the object and in the object itself. So the roughness is going to cancel out, and all I'm seeing is the difference between what the object was when I made the hologram and what the object is now. And so in the real-time technique, I can just look through here and I can deform the object and see the fringes change. And we know that between adjacent fringes, the optical path difference, if we, in going from the source to the object to the viewer, changes by a wavelength in going from one fringe to the next fringe. So if I know the geometry of the setup here, I can rather precisely calculate how much the object has been deformed. Okay. So this is what we call real time. So I've made the hologram, processed the hologram, put it back in place, and in real time I'm watching the fringes change as I deform the object. The other approach, and second approach here, is called double exposure. Have any of you done holographic interferometry? You made holograms? Good. Sometimes you do it even if you don't want to do it. Sometimes you do double exposure and you don't even want to do it. We'll talk about that. What double exposure holographic interferometry? Well, it's the same as real time, except now what we're going to do is we're going to take this object, we're going to make a hologram of the object, we're going to deform it and make a second exposure. And so we have recorded two images of the object, one before deforming and one after deforming. Now when we go through the reconstruction process, we will take the object away, just illuminate the hologram, and now look in here, I'm going to see two images of the object, one before deformation and one after. That's why I said some of you may have done this even when you didn't want to do it. Sometimes something happens during the exposure and the object moves or the object deforms. And I know the first time I did holographic interferometry, I didn't intend to do it. And I got my reconstruction, I saw these fringes on it, and I couldn't figure out what in the world produced these fringes. Okay. The advantage of double exposure is that you have no critical replacement of the hologram after processing. I mean, that's the real problem back here in the real time. If I make my hologram, I take it to the darkroom, I process it, and I bring it back, I have to put it back in the same location to within micron or so. Otherwise, if I have a rough object here, otherwise I have this rough object and the image is shifted sideways and the roughness no longer cancels out. That's where the holographic, the thermoplastic camera became very, very useful. With double exposure, you don't have to do, there's no critical replacement of the hologram. But the disadvantage here is that, I make a hologram, double exposure, before deformation and after deformation, and that's it. With real time, I can change the deformation during the reconstruction process, and I have a continuous comparison of the surface changes relative to the initial state. So actually, real-time holographic interferometry is generally preferred to double exposure, but the advantage of double exposure is that you don't have this critical replacement here. Okay, any questions? That's right. That's where the thermoplastic is just, it's so great. Once you use a thermoplastic camera for holographic interferometry, you never want to go back to film again, because you just set it up here, press a button, and it does the exposure and the processing and everything, and you look through it, and there it is. You don't have to take it away. You don't have to put it back in place. It's great. And if you don't like it, you erase it and do it again. It's too bad they're not, Newport's not selling it anymore. Well, I have some results here that I stole from various books. First is I guess it's just a cube of aluminum that the temperature was changed. And looking at this, there's no way you can tell, was this double exposure or was this real time? You can't tell. It doesn't make any difference here. But anyway, we have fringes here that show you how the size of this cube have changed between either one exposure and the other, or between the exposure and the readout of the hologram. And if you knew the geometry of the setup, you could precisely calculate how much the size has changed. And on the right side here, I just have some honeycomb construction panel that was debonded. And again, you know, you change the temperature or you put a little stress or something on it, and you expect the surface to change a little bit, but then you see places here where it changes a lot, so you know you have a problem. Okay. Another picture I have. This is one that I would guess was a, well, I say double exposure. I would guess a pulsed laser was used to do this. And we have air flowing past this cone. And I think first the hologram was probably made without any air flowing past it. And then the air currents were set up to see it flowing past it, and you see the density changes of the air. One on the right here is, I think, you know, a hologram was made without the candle being lit, and then the candle is lit, and we're not using the light from the candle, but what we're observing would be the heat from the candle changing the index of the air going through here. So this was illuminated from, both these would have been illuminated from behind, and we're looking at the light transmitted through this air here. Next one, we have a couple of light bulbs we're looking at. So again, illuminated from behind, so we're viewing through here. And first, the light bulb was not turned on. And then the light bulb was turned on, and the gases inside would heat up a little bit. And we could see the index variations in the gas very nicely. And these pictures look fair on the TV monitor. They look better on the piece of paper, but the original ones look even better than that. Get some very pretty patterns here. Next one is tire testing. And I remember when I was a graduate student, a friend of mine was trying to tell me there was good money making using holograms to test tires, but I didn't listen to him, so someone else did it. Anyway, the idea here, you take a tire and you pump it up and you make a hologram of it. And now we will change the pressure of the tire a little bit. And so you would expect the tire to deform a little bit. But if we look here closely, we'll see regions like here and here. And I don't know if you can see that very well on the monitor or not. You see there are a lot of fringes here and a lot of fringes there. So that's detecting weak areas in the tire. And I think this is used a lot now on the tires for airplanes. It's worked out. It's a pretty good way. So, you know, kind of the beauty here, this works on real rough surfaces. It doesn't have to be a specular surface. In fact, you almost don't want it to be a specular surface because you want light to get a picture here. You want light to get from the object to the hologram. And if it's a specular surface, the light might illuminate that and go off in some other direction. So diffuse surfaces are really nice. They will scatter light all over the place, and you'll get some in the hologram plane here. And you can measure deformations very well. It's a very powerful technique. Well, I said there were 3 types of holographic testing that we were going to do. We did the real time, we did the double exposure, and now we're going to do the time average. And this again is one that I'm sure the first person who did it by accident. Carl Stetson, I think, was his name. Well, he was the first to publish it. I don't know if he was the first to observe it or not. But the idea here is that we're going to make a hologram of some object that's vibrating. And the vibration is not large, it's a few wavelengths. And if we kind of think here for a second, then we'll look at an equation, but we think here for a second, this surface is vibrating, and so it's going to tend to wash out the fringes. Okay? And we're saying we're making an exposure time that's long compared to the period of the vibration. So it's going to tend to wash out the fringes. If you have nodes on the object, so you have places where it's not vibrating, then the fringes will not be washed out. And so you get a very bright reconstruction there. Where the fringes are entirely washed out, you're going to get no reconstruction. And when fringes are partially washed out, you're going to get a reconstruction but not very bright. And so probably when we look at the image, a hologram image, we're going to see superimposed on that interference fringes. And these fringes are contour lines of equal vibration amplitude. Brightest areas will be where there's no vibration, and then there will be certain areas where the fringes will completely wash out, and that will correspond to a dark fringe. Okay? So let's look at the equation for this. So from the handouts here, what I had is I just have some surface here that's vibrating, okay? And it's vibrating sinusoidally or cosinusoidally with time. And regardless what type of vibration we have, we could always write it as a Fourier series, a bunch of sines and cosines. And the amplitude of this vibration here is a function of position. So at the end, this thing is fastened down, and so there's no vibration. We have a node, and then here, the amount that it vibrates, the amplitude depends on where we are. So we illuminate this with light, and let's illuminate at normal incidence so we don't have to worry about cosine factors. And so the phase of the scattered light will go as 2 pi over lambda times d of x cosine omega t, and then a factor to illuminating at normal incidence, and so we're going through this twice. So this is how the phase, and there's also some phase change due to reflection on the surface, but that's going to remain the same as this vibrates back and forth, so I won't worry about it too much. And so the object here is some complex amplitude times e to the I phase. Okay. So now we're going to make an holographic exposure. We're going to record our recording material. And so we have our normal expression here of object beam squared, reference beam squared, object beam times complex conjugate of the reference beam, and reference beam times the complex conjugate of the object beam. And we're going to make we're going to integrate this over the exposure time. And for simplicity, I will make this equal, the exposure time equal to the period of the oscillation. And what really happens in practice more often is that you integrate over many, many periods of oscillation, and maybe it's many, many periods of oscillation plus a fraction of a period, and so the results are essentially the same as integrating over one period. So we have to integrate this thing over a period, and so we have all these terms here. But the term of interest, the term that's going to give us our primary image, is the OR complex conjugate. So the term of interest here will be integral of e to the I delta of x and t, delta being 2 times 2 pi over lambda d of x cosine omega t. And we will integrate that over one period, and I would normalize that by dividing by the integration time. And the integral here, I won't show it, but the integral of e to the I cosine omega t, I'm sure you've had this in other math courses, e to the I something times the cosine of omega t gives you a zero-order Bessel function of whatever the argument of the whatever was multiplied times the cosine of omega t is the argument here. So it's a zero-order Bessel function of 2 pi over lambda 2 d of x. And so the irradiance of the image will go as this zero-order Bessel function squared. And what does the zero-order Bessel function look like? Well, if we square it, it looks like this. If d of x, oops, 2 pi over lambda, this looks like my, somehow I'm missing a line here. So it goes as j naught squared of 2 pi over lambda 2 d of x. Goes, well, it starts out if d of x is 0, that's 1. So this would be where we have the nodes, where there's no vibration, the fringe is not washed out, and we're normalizing the intensity to 1. Now, as the amplitude of the vibration increases, the fringes are going to tend to wash out. And so the monolight in the reconstructed order for that particular location is going to become less and less until there's a certain amount of vibration amplitude here where the fringes are completely washed out. Okay? And so that's going to be a dark fringe. Now, if the vibration increases beyond that, the amplitude increases, the fringes are going to tend to come back, and we'll get a little bit of light in the reconstruction. Not nearly as much as what we got where we had no vibration, but we'll have a little bit of light here. And then as the amplitude increases still more, there will be a point where the fringes will wash out again, and we get 0 light here, and so on. So this is how the intensity of the reconstruction will look as a function of the amplitude of the vibration. So if I take here a plate that is vibrating, and at the edges here, I don't know how well you can see that. Can't see it at all well, can you? Yeah. Another eye test here. You can go back and look at the view graphs that you got, and you can see it a little better in the view graphs. Here, it's very intense. So this is where we had essentially no vibration. Vibration increases as we move along here. So this would be our first 0. Here, the light comes back a little bit. And so this would correspond to a point like this on our curve. And then we go to another 0. And then we get another little maxima here, this point here. And then back to 0 again, and then it's coming back in the middle, not that you can see it very well. So by knowing the geometry of how we set this up, and assuming we're at normal incidence, we could, it turns out to be very simple, that by looking at the intensity here as a function of position, we can determine what the amplitude of the vibration is as a function of position here. Okay, any questions on that? We have, if you go back and look in the literature, you'll find all kinds of beautiful pictures that people made using this technique. And this is just another one. Looking at some drum or whatever. This is one mode of vibration. Unfortunately, you probably can't see it too well on there. But there are fringes inside of here. So that's one mode. Here's the other. Oops, I'll move it over here. The other mode. And then they switched the two modes together. Vibration and got this pretty pattern. And I'll guarantee the original pictures are 100 times prettier than what you're seeing on the TV here. And then the last one is, yeah. See similar shapes in nature, yeah. This is one that's, well, Carl Stetson, who was the guy who first began publishing on this, was a great lover of music. And if you visit his house, he has all kinds of musical instruments there. Anyway, he ended up doing his PhD dissertation on his time average holography. And here we have some results that he had for a guitar. But anyway, he was trying to understand what makes a good sounding instrument. When does an instrument sound good? When does it not sound good? And he was trying to determine that using holography. And I think the conclusion he came to was that an instrument that sounds good gives beautiful interference patterns. No, that's the other way around. An instrument that sounds bad gave beautiful interference patterns. And instruments that sounded good gave lousy interference patterns. And so I think his theory had something to do with the harmonics. The good-sounding instruments have a lot of harmonics, and that was messing up his fringes or something. So anyway, if you have a lousy-sounding guitar, it probably would produce great holographic fringes. So don't throw it away. It might still be useful. And a number of years ago, I used to teach a course here in holography, and we had a lab that went with that course. And I remember one guy brought in his guitar, and he was showing what beautiful fringes was. And it certainly, when he played it, it did not sound very good. So I was glad it gave such nice, beautiful fringes. Anyway, well, that's everything I was going to say about holographic interferometry. The next thing I want to say a little bit about displays, and this has been an area that has worked out very well in holography. And so let's first, I'll say a little bit about a reflection hologram, and then we're going to talk about other types of holograms that people have made over the years for displays. And we'll talk more about volume holograms, I guess, on Thursday now. But one way that people have made some beautiful display holograms, maybe if we can just zoom in on the top one here. This again comes from Goodman's page 322. The idea here is that we're going to make a hologram, and the reference beam is coming from the left, and the object is placed right to the right here. And so the light goes through the recording material to the object, reflects off that, and this becomes a reference beam. So we're forming a hologram with the light from the object beam going this way and the reference beam going this way. And so we're getting very finely spaced fringes in here. And if this material is thick enough, we're going to get several fringe planes in here. And it's sort of like a multi-layer thin film. So now we come back, when we reconstruct this, we could reconstruct it with a laser source if we want. But we can actually reconstruct this one with a white light source. And the reason is that these fringe planes are going to reflect light only at the appropriate wavelength, such that we get constructive interference. It's like a thin film, it's like a filter, thin film filter, okay? And so we might illuminate this with white light, and we might just get blue light or green light reflected back here, and we'll see the object in blue or green. And typically these will have a band pass of well, for 15 micron thick film, it's a band pass of 100 angstroms or something like that. It's not too large. Works very well. It's just like using a filter with your source. Okay. So a lot of pretty reflection holograms are made this way. And I haven't been over to the planetarium in a year, I guess. But I think if you go over there and look in the display area, you'll see some of the pretty reflection holograms. And they're just multi-layer filters built into the hologram. Now, one problem people have gotten into here is that when they make this hologram and they process it, say they make it in film, going through the fixing and stuff, you take some silver out of the material, and then when it dries, it shrinks. And so we make this using a helium neon laser, and we try to reconstruct using a helium neon laser, and there's not much light. In fact, you can watch it as it dries. You'll see light, and then suddenly it'll disappear. And as you mentioned, it will shrink, the planes will get closer together, And so it's going to reconstruct at a shorter wavelength. And so you make it in the red and it reconstructs in the green, for example. Okay, so that's kind of neat. If you have time, you should go over to the planetarium, and I hope they still have the holograms over there on display. Yours went into the UV. It completely disappeared. Okay. I used to make these, reconstruct with white light, and you watch them as they dry, and just watch the wavelength change. And from the red to the, hopefully not to the UV, but the shorter wavelengths anyway as it shrinks. Okay, so that's a reflection type hologram. Now, the next thing is, I can see right down here, holographic stereograms. I said, you know, people were dreaming of these 3D movies, holographic 3D movies, and holographic television. And the problem there is that you have so much information involved. And so the idea is, can I some way reduce the amount of information? And if we're looking at an object and we're looking at, you know, three-dimensional thing, we're seeing it because we have two eyes. We're looking, you know, right, two different views here. And so we're seeing parallax in this direction. And so probably we could throw away all the parallax information in the vertical direction, and it won't bother us at all. So people developed these holographic stereograms that did just that. So the idea here is that we're going to take a lot of pictures of something, okay? Pictures from different angles. So we're going to get a lot of stereo pairs. And now when we make the hologram here, we're going to make the hologram the other way, this way. So we have a lot of pictures of things that as we walk around the room or something rotates maybe. And we're going to take this projector and illuminate a diffuser here so we get light all over the photographic plate. And we're going to take the photographic plate and illuminate it with a reference beam coming in here. And in front of the plate, I'm going to put a little slit. Okay? And record just a little bit of the hologram at a time. And so then I'm going to make a recording. And then I'm going to move to a different picture here and move a slit sideways, make a second recording. Change the picture, move a slit sideways, make a third recording, and so on. So my recording here is going to be made up of a bunch of slit holograms. And now I come back here and I'll process my film and put it back in place here. And what I really have then is a hologram of a bunch of stereo pictures, stereo pairs. And I come back here and I look through my hologram, and this eye will see one picture of this pot, say, and this eye will see another picture. And so I'm going, and these pictures were taken from different angles, and so I'm going to see three-dimensional effects here. And as I move my eyes around, I'm going to see a different set of stereo pictures. If I move my eye up and down, things don't change much. I've lost all the parallax information in the Y direction, and I have only in X here. But that probably works okay. So we have greatly reduced the amount of information that would need to be transmitted here if we transmit it over a TV channel. So this is what we call a holographic stereogram. Any questions on that? Has anyone made any of these? No? I haven't either, so it's okay. No, that's coming up. That's next class. Blowing the kiss will be that's coming up. That's it's similar, but the kiss is very, very clever. We'll get to that. The next one I want to talk about is rainbow hologram. This I absolutely love. This is made by, well, invented by a person by the name of Steve Benton, who used to work at Polaroid. he had a fantastic job at Polaroid. He had a great laboratory, all the equipment you could possibly want, unlimited budget, and he could do anything he wanted. Okay. He was a friend of Ed Land, who had started Polaroid and was the head of it for many years. He also married the niece of Ed Land, too. But he had a great laboratory. Anyway, he invented this thing called rainbow holograms. And I said I used to teach a course here in holography, and we had a lab that went with the course. We nearly went bankrupt making rainbow holograms. They were so much fun that the students made so many of them that it cost a fortune here. Actually, it wasn't that bad. It was a lot of fun. These are really neat devices. So what we're going to do is to make a hologram here, and we're going to have a hologram that we're going to be able to reconstruct using sunlight, tungsten bulb, flashlight, whatever you want. You don't need a laser here. And it's going to be beautiful, three-dimensional, and whatever. And we probably won't, well, I don't know if we'll have enough time to cover it all here or not today, but we'll finish it on Thursday if we don't finish it today. The idea here is that we have some object back here, and we're going to make just a regular hologram of that object, okay? Diverging reference beam, transmission hologram. Okay, step one. Now what we're going to do is that if I take this hologram, so I process this hologram here and put it down here, and I'm going to reconstruct the hologram with the conjugate of the original reference beam, okay? And so if this is a diverging beam, this means I have to have a converging beam here. So I have a source here and I have a big fat lens there, okay? And it's going to produce an image, right? It's going to image the source here. So I'm illuminating it with a conjugate. So it's going to produce a real image of the original object. Okay? The real image is here. Everyone got that? Then over this hologram, I'm going to put a slit, a narrow slit here. Okay? And I'm still going to get this image, but it's going to be an image that is just formed by the light going through that narrow slit. Then I'm going to make a hologram of this image here. That's what I'm doing down here. And I'm making this hologram with a beam that's converging to this point here. So it's a converging beam. I'm making a hologram of this here. Okay? And by the way, you know, I'm making a hologram of this. I'm also, at the same time, making a hologram of this slit. Okay? Now I take this hologram and process it. And this is going to be a rainbow hologram. So now we take this hologram, process it, made it with a converging beam. I'm going to reconstruct it with a diverging beam. And when I reconstruct it with a diverging beam, and I'm running out of time here, I will get an image of the flower pot here. And I also will get an image of that slit. Okay? Now, and I put my eyes over here where the slit is, and I will see this object. Now let's say I reconstruct this with a single wavelength. I get a nice image of that slit there. If I move my eye up here, I'm no longer going to see the object because the light is all going through that slit. And in 20 seconds left, I can't finish it, but what we'll do next class is we will use a white light source here, and then what we're going to see will be many images of a slit, each with different color. So we'll finish this on Thursday. So I'll see you Thursday morning.